We're back again for another awesome, amazing, life-changing Numpy tutorial. I keep saying I'm going to talk about dot products. Well, this time I'm actually going to try to. Dot products are extremely useful for, they're probably the most common operation that's done in 3D calculations. Maybe other than like plus and minus or something, but dot products are everywhere. You need to understand what they are and how to use them to do anything important or anything complex. Or you at least need to have somebody in your team who knows how to use them, so you can make them do it. So a basic idea of a dot product. Let's start down here in our interactive console. And, you know, if you haven't done it already, you got to do the whole import numpy as np thing. And now we want to have we're just going to start with the simplest example. So we're going to do np dot x equals np dot arrange 3, and now x is it's a single 3D vector. So we'll pretend like that's one vertex location. Now a dot product is the same thing as the Pythagorean theorem, but in 3D space. And you can look up the Pythagorean theorem and you'll see what it does. And it sounds fancy, it's actually pretty simple. If we did the dot product of x with another, so let's make y equals np dot arrange, and it's going to be 3 also, but then y is going to be added to, so we're going to say y plus equals 2. And now this is x, 0, 1, 2, and this is y, 2, 3, 4. And to get the dot product, we're going to take, what the dot product does is it takes the first element in the first array, multiplies it by the first element in the second array, the second element of the first by the second element in the second, and so on. So 0 times 2, 1 times 3, 2 times 4. And what it would be is 0, 3, 8. And then, so you have this 0, 3, 8, and then it takes 0, 3, 8, and it gives you the sum, which is going to be 11. So if we do np dot, you can do np dot like this, and you can put your two values in there, x and y, and it's going to give you 11 because of what it does. This times this, this times this, this times this, and then the sum of all those values. And it's kind of weird. It's like, well, okay, well, what would be the point of that? Well, when you're in Euclidean space, or you're in, 3D space on pretty much every computer, you have the x, y, z values of stuff, and as long as you're dealing with values that are aligned to the x, y, or z axis, you can do calculations on those axes and figure stuff out. But as soon as you have something that's not aligned to the x, y, and z axis, you have these values that are this weird mix of x, y, and z. Well, the dot product allows you to overcome that issue and still do these kinds of logical checks and different things with these arbitrarily pointing vectors or axes or whatever, however you want to think about them. So for example, like if we look at the normal of this plane, you can go down here, turn on normals, and you get this line that's perpendicular to the plane. In order to figure out, like say Suzanne's still afraid of water, and we want her to stay above the water, but we're on a planet that has isolated zones of gravity divergence, or I don't know. They have stuff like this in video games all the time where gravity points the wrong direction. If we wanted to know if Suzanne was below this plane, well, we can't do that by looking at the z value, or the y value, or the x value, because the x, y, z values are all sort of mixed when things are at these weird arbitrary angles. And if you take the line that's perpendicular to this plane, or its normal, it's also going to be a mix of x, y, z values. So let me just show you here. I'm going to say ob equals bpy.context.object, and we want to get ob.data.polygons and there's only one polygon in this object, so we're going to say polygon 0. And then dot normal. And it's this vector which has 3 values. Its x value is 0.05 something, and its y is 0.6 something, and so on. Well, the question of how would we know if any of Suzanne's vertices are on the other side of this plane becomes more complicated with these arbitrarily rotated vectors, and the answer is to use the dot products. So let me tell you essentially what the dot product is really useful for. First thing it's useful for is to give you the length of something. So I'm going to have a vector here, and I'm going to just show you what this vector looks like. So this is my 3D vector. We're going to use this edge segment, and say we want to know how long this edge segment is. Well, all we have is this value up here, this x, y, and z. That's all that we know so far. But we can use the dot product to get the length of this. So I have my measure it tool. I think I showed you this before. So I know that this plane, vertex number 4 is the one that I'm looking at. So we're going to do ob equals bpy.context.object again. And now ob is a reference to this object. And I'm going to say v equals ob.data.vertices 4, and now v is this value. Well, it's this vertex, and then I'm going to say v.co, and v.co is another one of these 3D vectors that you know, just has a whole bunch of numbers. These are 64-bit float values. And how to get the length out of this one, initially you look at that, it's like, well, I have no idea. Well, it's not that complicated. Remember, Pythagorean is a squared plus b squared equals c squared, and it's talking about, you know, the hypotenuse of a triangle, and it's talking about an x and a y value. Well, we have an x, y, and a z value, so we have to do a squared plus b squared plus c squared is equal to d squared, or whatever. In this case, it's equal to the length squared. So if we square all these values and then we take the sum, we get the length squared. And dot product just gives us the length squared. So we do v.co, and let's make it a Numpy array. So we'll do np.array. So x equals np.array. We're going to convert this v.co into an NP array, and now we have the exact same values, but as a NumPy object. And actually this vector up here is a double precision float, and this is a 64-bit float. Just a minor technicality. So if we do x dot, well, there's several different ways we can do this. We can do np dot, and we can do x, and we're going to dot x with itself. Well, we get this single value that is the squared length of x. And if we want to know the length, we just get the square root. So we can do np dot square root, which is sqrt, and then we can do np dot dot and xx. And this gives us the length of this vector. This edge segment here ends up being 5.938 something. That's our actual final total length. So dot products are the squared length of vectors. Well, that's fine, but what if you had like this vector here, and I want to take the dot product of this value and this value? Well, what does that mean exactly? Because it's not going to give you a length, because you're dealing with two vectors here, and You know, are we getting the length of the first one? Well, no, because that would be the dot product of this one with itself. We're obviously not getting the length of the second one, because that would be the dot product of that one with itself. So we're getting this other number that has some meaning, but what its meaning is sort of unclear at this point. Well, let's talk about what that means. So, first of all, we need v1. So v1 is going to be our vertex number 4. So v1 equals np.array ob.data.vertices 4. So here's v1. v1 equals np.array ob.data.vertices 4. Sorry, .co. Don't forget that part. Now v1 is this. It's the location of this vertex, which is 304 something. 304 something. This here, it doesn't even need to be here. This is just here for a visual aid, so you get the idea that this is an edge segment. If this was over here, well, we would need to get this edge segment first by taking this value and subtracting this value, and that would give us this edge segment as if it were here. It basically moves it down so that its origin is at 0, 0, 0, so that we can work with it. And anytime you want to get an edge segment, you have to do that step first. You have to take the destination and subtract the origin, and that moves everything down to where this is now has an origin of 0, 0, 0. I think I did that in one of my earlier tutorials, but we'll get to that also. We'll do some examples of it. So we have v1 now, which is vertex 4. Now we need v2, so we're going to do v2 equals vertex 6. Now v2 is the location 306077 whatever, which is this vertex here, 3677, right there. Oh, and I just moved it up and down. Hey, that's cool. I didn't know you could use a mouse wheel for that. Ooh, what did I do there? I don't even know. Make that a little larger so you can see it. Make this a little smaller so you can't see it. Alright, yeah. So there's my x, y, z values. And I think I have to do this again since I moved it. v2. Yeah. So it should match v2 equals np. Oh. Now it should match. Sorry, things are kind of quirky when it comes to updating and popping in and out of edit mode and stuff like that. If you try to access vertex data on an object while you're in edit mode, it's not necessarily going to give you the correct location. So whenever you're working with Blender and you're in edit mode, switch back to object mode first before you access your object data, like vertex locations, or it can give you different values if you've changed something while you were in edit mode. So v2 theoretically should be identical to this, so -3.6147, -3.6147, and it is. Now let's talk about what happens if we get the dot product of vertex 4 and vertex 6. Well, np dot v1 and v2. And I'm just going to say dot equals. Well, dot is this new single value of 20, and it means something, and it relates to these two vectors, and it relates to the relationship between these two vectors in some way, but how is like unclear still. Well, what happens if we move this down to where it's like on the other side? So you'll notice that with a plane, the normal of this plane is exactly perpendicular to the plane itself. Now, if we pretend like this value here, this vertex 4, is the normal of a plane, and let's say we had a plane here, and this is the normal, so it's perpendicular to it. As soon as this moves to a point where it would be on the other side of that plane, something interesting happens with the dot product. So right now we're on the positive side of this plane, and you'll notice our value that we got for the dot product of these two is a positive value. Well, as soon as you move it to the other side of that plane, pretend like there's a plane here, now v2 equals, we have to update that, and now we do the dot product of v1 and v2. Dot is now a negative value. So one of the simplest things you can do with the dot product is to figure out which side of a plane, an infinite plane, something is on. So let's just do that real quick with Suzanne. And this will take a little bit of thought. Hopefully I can go through it quickly and it'll make sense. So first thing, we've already got Suzanne's z values, which are, we'll rewrite this. Okay. So remember, the z values from Suzanne are, let me turn this off real quick, are indexed by slicing into the array of vertex locations from Suzanne. Print CO, all for 10, gives you, now our active object is currently Suzanne. It gives us, you know, the first 10 vertices, so you can see that. And then if we print z is the z values, all for 10, we get the first 10 z values, which are, you know, whatever her z values happen to be. And, you know, you move that, then they change. Now what we're going to do here, we want to take the dot product of all of Suzanne's vertices with the normal of this plane. So we're going to take these vertex locations here, and we're going to get the dot product of those vertex locations with this perpendicular line here. And it's going to be a little bit tricky, and it's easy to get confused, the order and steps and things. So keep that in mind and think about that for a second. And real quick, I'm going to show you something else. So remember we did np dot, and we did v1 and v2. Or we can do v1 and v1, and it'll give us the length squared. And we can do the square root of this to get the final length of that vector. There's another way to do dot products that is faster. And there's ways to do dot products for multiple dimensions, and there's lots of ways in Numpy to express dot products. You can do like v1 and then just run the function directly as an attribute of v1. Since it's a Numpy array object, one of its attributes is actually, there's a few functions you can do this way. So you can do dot dot and not bt, dot v1, and if you do v1 dot v1, it's the same thing as doing np dot v1 v1. Or you could do v1 dot v2, you know, some other vector, and it's the same thing as doing np dot v1 v2. The way that I usually write it, given I've done a ton of speed testing, and doing v1 dot v2 I think is the same speed, but if you're dealing with like an array of vectors and you want the dot product of an array of vectors with another single vector, you can use this symbol that's sometimes used to indicate matrix multiplication, and you can just do v1, and you're using the @ symbol to indicate matrix multiplication. So v1 at v1 is the same thing as v1 dot dot v1, which is the same thing as np dot v1 v1. My preferred way of doing it is v1 at v1, or v1 at v2. That's the way that I like to do it, and that's primarily because, let's say you had an array of vectors. X equals this, and x dot shape equals 4, 3. And I wanted to, let's say I wanted to take the dot product of every row here with a single vector like v1. Well, I can do that very easily by doing x at v1. And it will go through every row here, and it will give me the dot product. And so I get 4 dot products here, 1 for each row, and that dot product is actually the dot product of each row with v1. That's why I prefer the at symbol. And if you're using dot products and you did like np dot, and you do x and v1, you get identical results, but x at v1 gives you the same thing, and it's actually considerably faster. I don't know why exactly. It has to do with how Numpy is set up, so this is better performance than using np dot to just do x at v1. Now, you've got your multidimensional array, and you've got your one-dimensional array. You can't do your one-dimensional array and a dot product with your two-dimensional array. You have to start with your multi-dimensional array first, and then multiply it by your one-dimensional array for this to work. So some nuances to be careful with. But for now, all of that said to say, wherever you can, use Numpy matrix multiplication like this. It's easier to write, and in certain cases it's actually the fastest way to do it. If you use einsum, which we'll get into later, it's identical in speed to doing it this way, but it allows you to mix different dimensions of arrays and get dot products in different configurations and get sums in different configurations. Numpy.einsum, which if you're brave you can go and just look it up, actually is the most robust way to get dot products for various combinations of different dimensions of arrays. For now, we're just going to use the at symbol for all of our dot products. Now, getting back to Suzanne. So, we want to know, we want to use one of the simplest things you can do with dot products, and we want to know, are we on the positive side of this plane, or are we on the negative side of this plane? So we need to take the dot product of all of Suzanne's vertices with the normal of this plane, which is this guy right here. So first thing we want to do, we want to take, let's see, we'll call this object by name so that it's a little bit easier. And let's see, this object's name is Suzanne. So we're going to say, we can get rid of this. I'm going to say ob, actually we'll say monkey. Monkey equals dpy.data.objects Suzanne, and this is a plane, and its name is plane. The plane in Spain falls mainly on the brains of the Dane who, we're going to name it plane with a small p. And we're going to say plane equals that. Alright, those are our two objects. So monkey co, monkey do is going to be monkey, and we don't really want the coordinates of the plane, we want its normals. So we're going to say plane. Actually, let's just say normal, because we know we're working with the normal of the plane. So nor equals, I won't be that lazy, normal equals plane dot data dot polygons 0 dot normal, and we actually want to make this a Numpy array, so we're going to say np dot array, and now we want to print monkey CO, just a few of these, and we want to print, I'm doing this to make sure that we did this correctly, and I can already see I did this incorrectly here. This should go outside of the argument, obviously. Am I printing anything else? Yes, I'm already printing that. And this is going to throw an error. Alright. Plane is not defined because I spelled it wrong here. Now, OB is not defined because we no longer have OB. We have monkey. Now, CO is not defined because it's now monkey CO. Now, we have everything. Okay. So, we want to get the dot product of all of these locations with the normal of this plane. Well, here's the first problem. And let me just show you something. If we take the normal of this plane, I'm going to show you where the normal is. So I'm going to take this normal and I'm going to write it to this edge down here. Now remember, this is vertex 4. So I'm going to say MO, let's see, that one's plane. So plane dot data dot vertices 4 dot CO now equals normal, because normal is the plane CO. And then I'm going to do plane dot data dot update. I don't remember if I have to do this, but I'm going to. And this is what you end up with. This is what the normal of this plane looks like. So here's the normal, but when you take the normal and you input it as a location, it's down here. And it's like, well, why is that? Well, the reason that is because the normals are not out here in space anywhere. They don't have some origin out here. When you get the normals of an object, you don't get the normals plus the origin. You get the normal starting at the 0 vector. So you can think of a normal as just a direction. You'll notice that it's pointing exactly the same direction as the normal, because it is the same direction as the normal. It just doesn't have the same origin as this blue line out here that's drawn for your convenience. What I believe they're doing out here is they're taking the mean location of all of these guys, which you can see where the cursor would appear at the average location of all those guys, and they're using that average location as a place to draw this blue line, this normal, so that you can see where it is relative to your planes, just so that it makes sense. This is just a visual aid. But what you're getting with the normal is the normal without the origin. Well, that's a problem because our plane is not at 0, 0, 0. It's out here arbitrarily somewhere in space. So in order to get the origin in a way that matches the location of this plane, we need to find a way to make Suzanne relative to this normal down here, taking into consideration the location of this plane. There's probably a better way I could say that, but hopefully you get the idea. So let me think about this for a second. Basically what we can do is any one of these points that's on the infinite plane can serve as an origin. So if we take Suzanne's vertices and we subtract Suzanne's vertices from any vertex that's on the infinite plane of this object, of this plane, so it could be, you know, any one of these points as long as they're on that plane. Really, it just has to be on the plane for the exercise that we're doing. I'm just going to pick one randomly. So I need to see what this number is, for example. And my measure it tools, where did they go? That's not it. Did my measure it tools go away? .3D printing, display, oh here we go. Okay, so my measure it tools, this is, we'll just do 0 actually, because 0 is fun to work with. Alright, so we're going to use this as the origin for our normal. And like I said, as long as it's on this same infinite plane, any point on that plane would work as an origin, if I'm thinking about this correctly, which I believe I am. So we need to get the dot product of Suzanne's vertices with an origin that it originates on this infinite plane with the normal of this. So it's going to take a couple of steps. First thing we do, we need to get our, we've got our normal, now we need an origin. So we're going to say origin equals, we're going to do something similar to this up here, so I'm just going to copy it. So origin equals np.array plane.data, and we're going to do vertices 0.co. So we're taking the coordinates of CO. And remember, with Numpy, you can do, like, you know, here is x. We can do x minus v1, and it will do a row-wise subtraction. And it will take all of these rows, and it will subtract v1 from all of those rows. And you end up with this logical value where, you know, 0 minus negative 3.9 is obviously 3.9, 1 minus, and so on. We covered that in an earlier tutorial. Alright, so we need to do CO. Let's see. We're going to say vex because it's kind of like converted again into vectors. Equals mo CO minus origin. And now we're going to do, remember that our vex, if we print our vex, it's this array of 3D vectors. Get rid of this, get rid of this, and so here's our array of 3D vectors, because we've taken the vertex locations of Suzanne and we've just basically moved them as if this vertex here in our plane were location 0, 0, 0. So we've pulled the data, we've pulled a bunch of edge segments essentially that go from between here and every one of the vertices here, and we're going to take this imaginary edge segment between here and all these vertices, and we're going to get the dot product of it and the normal. Okay, so now we want to do, we start with the multidimensional array, vex at normal, and we're going to say dot equals vex at normal. So now if we print dot, this is dot e, the dot product. We get this single value for every one of these. So these are all these scalar values, and they're all fairly similar because it's basically a similar direction pointing out towards every one of these vertex locations. Hope that makes sense. Now, you'll notice that they're all positive. And that's because everything is on the positive side of the plane. But as soon as we start moving stuff over here to the negative side of the plane, when we print this, now we start getting these negative values. And it's anywhere these are on this other side, that's where you're seeing the negative values. So if we use our np.any or our np.all, we can actually test if any portion of Suzanne is on the negative side of this plane. And this is incidentally the basis for how you do the first step in collision detection also. So first thing I'm going to do is show you that if we add the normal to Suzanne's vectors before we set them again. So we're going to take I'm just going to get rid of this, and I don't want to print this anymore. And we're going to take monkey CO plus equals normal, and we're going to do normal times 0.02 to make it a smaller value. You can do 0.02 for clarity. Then when we run this, Suzanne is going to move in the direction of that normal. And if we point this plane a different direction, she's going to move in that direction now. So she's moving whatever direction this normal is pointed. Because we're simply adding that normal multiplied by some small fraction of itself to the location of Suzanne's coordinates. And if you had this set up to run on a frame handler or something, you could grab this normal and spin it around, and Suzanne would keep moving in whatever direction while it's spinning, and you can do some cool stuff with that. But for now, you just understand that we're adding that normal as a 3D vector to the location of Suzanne, and she goes in that direction. So now, let's say we want to check to see if our anti-gravity weirdness water, if Suzanne is on the surface of it or if she's below the surface of it. So right now she's got part of her face stuck in our anti-gravity water. And we need to check to see if any of these dot products are negative to know if anything is on the wrong side of this plane. So we can use np.any again. So if we do np. And we need to do it after we get our dot product. So there's our dot product. np.any dot is less than 0. We're going to say wet again, then she's wet. And now we're going to do if wet, then move up on the normal. And you'll see what happens here is if any of these dot products are negative, then she's going to move along the normal until none of these dot products are negative. So she goes in the direction of the normal, she gets to there, and she stops. And now that we've got this set up, it wouldn't matter which direction this plane is pointing. She's going to move in the direction of that plane until she stops. Clear as mud. She's not going to move, obviously. Now she's going to move that way. So there you go. There's your basic introduction to dot products. And this is the basis for doing cool stuff like closest point on edge, and for doing collision detections, and for orienting planes to other planes, and a whole lot of other cool stuff that you can do. So in the next tutorial we'll get a little bit more in depth on that, and we'll also set up a math playground. So I've got up here, let's see, consider using a scene handler to see updates in real time. I'll show you how to do that in my next tutorial, and that'll let us visualize our math a little bit more quickly and interact with it in real time. So I will see you in the next tutorial. Sorry for the serious tone, but I realize this is a little bit more mathy than they've been up to this point. I hope you're following along, and I will revisit some of this next time. So I will see you then.